Okay, so this video is all about Kirchhoff's laws. There are two of Kirchhoff's laws, the junction rule and the loop rule. The junction rule is also sometimes called the current rule. Tells us that the sum of the currents entering any junction must equal the sum of the currents leaving that junction. Loop rule is sometimes also called the voltage rule. And that one, we're basically going to travel around in one loop in the circuit, and the sum of all of the potential differences or voltages across each thing that we come across, like resistors and batteries, has to be 0. So we're going to go to this example problem here, and we need to define a few things before we can do anything with this problem. And the things that we're going to define are what the heck a junction is, and there's another term called a branch. So a junction is any place where two or more wires come together. We have two junctions on this chart here, on this circuit diagram. And I'm going to mark those with dots. So here's our first junction, and there's our second junction. Okay, next definition is for a branch. A branch is anything that connects two junctions. A branch is anything that connects two junctions. So this diagram has 3 branches. We have this top branch that goes like that. We have this middle branch, and we have this bottom branch. This circuit is different than anything we've looked at before because there are 2 sets of batteries separate from each other. You'll see the 24-volt battery here and the 12-volt battery here. And they're separate from each other, and there's a resistor in between them and all kinds of other good stuff. Kirchhoff's laws can be used for any circuit, but they must be used for circuits where there are multiple batteries like this that are separated from each other. For circuits like this, we're always going to start off with the current rule, otherwise known as the junction rule, and then we'll do the loop rule second. Any circuit like this, you're going to use both rules to come up with the answer. And the goal is always to find the current in each branch, or sometimes you may be asked to find like the current through one of the resistors. You can't do a combo circuit like what we did before to find that. So, one general rule, the number of branches you have is equal to the number of currents you have. So we have 3 branches here, which means we will have 3 currents. Every branch gets its own current. We will kind of randomly decide which direction those currents are going in, and in the end we'll get to find out if our random decision was correct or not. You'll see what I mean. That sounds a little weird right now. So starting off, I'm going to choose those 3. I'm going to call them I1, I2, and I3, and I'm picking a random direction for that. So I'm going to say that I1 goes in this top branch here, and it's going to go upward like that. So I put an arrow there and I write I1. And I can even put that on the other side just to remind myself that it's that same current over on the other side. I'm going to say I2 goes through the middle, and I'm going to say that it goes to the right. Again, I'm randomly choosing these directions. There's not really a whole lot of rhyme or reason to it. And I'm going to say that I3, which is in that bottom portion, I'm going to say that it goes downward here, which means that over through here it would be going upward. So that's the first task, is drawing those currents up there. And then we're going to go ahead and apply that junction rule next. And so let's look at this first junction here, the one on the left-hand side. The sign rule is that whatever enters the junction, whatever current is pointing toward the junction is positive. Whatever is pointing away from the junction is negative. So I1 is pointing away from the junction. So I'm going to write minus I1, or negative I1. I2 is pointing away from the junction, minus I2. I3 is pointing toward the junction, so plus I3 equals 0. Again, pointing toward is positive, pointing away is negative. Okay, so we're going to look at the other junction now. And with the other junction, I1 is pointing toward it. I2 is pointing toward it. But I3 is pointing away. If you look at those two equations, you'll notice that they tell you the exact same thing. Because if you take the top equation and multiply it by -1, you get the bottom equation. So when you have a circuit that looks like this one, particularly where there's kind of two chunks, there's a top and a bottom, as opposed to there being 3, we'll do a circuit where there's 3 of them. When you have one where there's only 2, you only need one of the junction rule equations, because the other equation doesn't tell you any new information. So that's junction rule. Now we're going to do loop rule. We need the number of equations as we have variables. So I have one equation already. I have 3 variables, so I'm going to need 3 equations total. I could do 3 different loop rule equations, because I could do the small loop up top, the small loop in the bottom, and a big loop on the outside. But I only need 2 of those. I don't need all 3. So I am going to do the top small loop and the bottom small loop. Okay. The thing that I need to decide is if I'm going to go around those loops clockwise or counterclockwise. It's just a random decision. Again, it doesn't matter which way you choose. But indicate it on your diagram with a little swirl like I'm about to do. So I'm going to go through these loops clockwise. And so I indicate the fact that I'm going clockwise with that little swirly. Okay, a couple rules here. With batteries, if you go from negative to positive, if you land on positive, you end on positive, it's a positive voltage. Again, with batteries, if you're going from negative to positive, you land on positive, it's the last thing you go through, it's a positive voltage. And then vice versa, if you're going positive to negative, you end on negative, so it's a negative voltage. With resistors, if you go through the loop the same direction that current is traveling through that loop, you have a negative voltage. Again, if you go through the resistor, if you're going through that loop through the resistor, the same direction that current travels through that resistor, it is a negative voltage. And then the opposite is also true. If you go through a resistor in the opposite direction the current goes through the resistor, it is a positive voltage. If you go through a resistor opposite the direction current is traveling through that resistor, it is a positive voltage. So I'm going to go ahead and do a loop rule. I'm going to look at that top loop up here. You can start anywhere on the loop as you're writing the loop rule equation. I'm going to start at this junction here, this junction on the left here. And again, I said I was going clockwise, so I'm going to start traveling upward. The first thing I encounter is a battery, really a set of 2 batteries, but I treat it as one. I'm going negative to positive, so it's a positive voltage, and that is 24 volts. And then I go through that resistor, this resistor right on top here. Now I'm traveling around in my loop, so I'd be going from the resistor left to right, and the current would be going through the resistor left to right. So it is minus, or a negative voltage, and I'm just going to put voltage of the 2 ohm resistor. I'll do more with that later. And then the same thing goes for this 4 ohm resistor. As I'm traveling through my loop, I'm going downward through that resistor, and the current is traveling downward through that resistor. So minus V of the 4 ohm resistor. And then to finish my loop, I travel through this 3 ohm resistor. This time I'm going right to left, but the current goes left to right. So I'm going in the opposite direction the current travels through that resistor. And so I say plus V of the 3 ohm. I got back to my starting point. I traveled through this. I'm back at where I started. So now I write equals 0. Okay, so now we want an equation that has currents in it. We don't want these random V's that are here, but we know V equals IR, right? So I'm going to use that equation, V equals IR, to write a new equation. Now I'm going to leave off units. You know that that's not common for me to do, but it's going to make life a lot easier if I just leave off units in this equation. So 24, I'm just going to write 24, not 24 volts. We don't do anything to that one. V equals IR for this 2 ohm resistor. The I that travels through that is I1, and R is 2 ohms, so minus 2I1. For the 4 ohm resistor, it's minus 4I1. For the 3 ohm resistor, it is plus 3I2, because I2 is now the current that travels through that 3 ohm resistor. And then equals 0 at the end. To get this equation, one more step to do with this equation is to combine like terms. Minus 2I1 minus 4I1 gives me minus 6I1. So I can write 24 minus 6I1 plus 3I2 equals 0. That's my second equation. I'm going to quickly go through the third equation. Third equation is going to be for my bottom loop here. I'm going to start in the top left corner at the same junction I started at before. And I'll use a different color for this one. The first thing that I encounter as I go clockwise around this is this 3 ohm resistor, and I'm traveling through it the same direction as current goes through it. So I have minus, and I'm just going to go ahead and write 3I2 this time. I'm kind of skipping over that first step I did. 3 is the resistance, I2 is what's traveling through it. And then I get to the next junction, I go downward, because I'm going in this bottom loop here. And so I encounter another resistor. It's a 1 ohm resistor, and I3 is traveling through it. I'm going through the resistor the same direction as current goes through it. So minus 1 I3. And then also minus 5 I3. That's my next resistor I get to. This down a little bit so I don't run out of room. And the last thing I come to is this battery.